that sound? Not too loud in the back there? Not too quiet? All right, great. So let's get started. Thank you everyone for coming. My name is Nick. I am a graduate student at the University of Calgary. I work with Dr. Matthew Taylor. Everyone else in my group seems to care a lot about theory and simulation and dwarf galaxies. I'm kind of the guy who builds things, and tonight I'll be talking to you guys about what we're building, which is the CASTOR, or the Cosmological Advanced Survey Telescope for Optical and UV Research. So, really simple name for this thing. But it's named after a beaver, which is a symbol of Canada, and, well, I'm going to tell you a little bit about what it is, also what UV astronomy is, and also in the first place, why do we want to put telescopes in space when we have perfectly good ground that we can put them on? So, for some context, CASTOR has been in development for about 15 years. Since about 2011, even earlier than that. We knew that we would eventually need a telescope to take over what's called the ultraviolet sort of observing role. And this was considered, back in 2020, the highest priority for astronomy in Canada, actually, by the Canadian Astronomical Society. So, hopefully, through this talk, I'll convince you a little bit about why it's important, why you should care, and what it's also going to do. So, let's just start with a simple question. Why do we do astronomy from space? We have telescopes right here, we have telescopes outside. Why spend all that money putting a SUV-sized piece of metal up there? It really comes down to two simple reasons. The first one is, what can we see? And the second one is, how well can we see it? There's also a third secret reason, which is it's just cool, basically. But I'm going to try to motivate the first two. So, a lot of you probably saw this either in school or on the cover of a Pink Floyd album, way back when. That's light passing through a prism. And what it illustrates is that light that you and I see really isn't just a single wavelength or a single kind. It's actually made up of different kinds of wavelengths. Light is a wave, most of the time, we're not going to get into that. And it comes in a wide amount of varieties. You can actually see many of them on the side right here. You have really short wavelengths, like gamma rays, and very long wavelengths, like radio waves. The longest radio waves can really be thousands of kilometers long, while the shortest ones, like gamma waves, are billions or trillions of a meter in length. Comparatively, like what we see is actually a really, really small portion of all the light that's out there. So the visible light spectrum, which is from about 350, like 400 nanometers to 700 nanometers, that's this little sliver out of all this stuff over here. It actually makes up less than 1%, even less than 0.1% of all the light that is out there in the universe. So if we try to observe the universe in just visible light, what your eyes can see, we miss out on the vast majority of it. And the unfortunate thing is that if we want to see most of the light that's out there, we actually can't do that down here even with our best sensors. Why? Because most of it doesn't actually make its way through our atmosphere. This is a so-called radio window. Radio light makes its way through. Visible light makes its way through the atmosphere, as does a little bit of infrared and a bit of UV. But for the most part, our atmosphere does a really good job of blocking this other radiation, which really is annoying for astronomers who want to see all this really high energy, cool light over here. But I guess if that stuff made its way through the atmosphere, we would die from radiation, so kind of a bummer. So how do we get around this problem? Well, you just put a telescope above the atmosphere. And we want to do that because, well, there's a lot of detail, like I said, that we would miss if we didn't look at other wavelengths. And that detail corresponds to structure and physical processes, sort of phenomenon that only occur in certain parts of that spectrum. This is an object called the Crab Nebula. It's actually visible in the sky tonight. You might see it with the Clark Malone telescope if you go look through there right now. And you see that in radio and infrared light and visible light, it reveals different parts of its structure. This thing essentially has a neutron star at the center of it. It's the remnant of a supernova. And if you look in X-rays, you can actually see the gas swirling around that object, as well as in gamma rays, how hot it's glowing. But if you look in visible light, you see all this other structure, these filaments of all the gas that was blown off during the supernova that occurred about 1,000 years ago. So that's really why we want to know about these things. That if you look in different wavelengths, it gives you different pieces of the puzzle of what is out there and how does it work. So another problem is that the air itself is pretty messy, it's turbulent. This is why stars twinkle. You have temperature gradients, differences in temperature, differences in pressure as you go through the atmosphere, and that makes the light waver. Like on a hot day, you might see the heat rising off the asphalt and the some image in the background wavering. That's what you have happening through the atmosphere. And that creates a sort of limit on how clearly you can see something. So let's compare, for example, well, one of the biggest telescopes on Earth, Subaru, yes, like the car, yes, like the Pleiades. And it's an 8-meter wide mirror sitting about 4 kilometers above the ocean on the top of Mauna Kea in Hawaii. This is an image that it took, and how clearly it can resolve this very small object in the sky. And compare that to the Hubble Space Telescope, which is a third to a quarter of the size, but it's 540 kilometers above the Earth. And immediately you see a really massive difference in how clearly you can not only see that object, but pick up other fainter objects and structures around it. So if you want a complete picture, you gotta not just look at different wavelengths, you've gotta look at, well, getting rid of the atmosphere. So that is when we come into space telescopes. And what do we have up there right now? Most of you, well, who here has heard of the Hubble Space Telescope? Raise your hand. Okay, thankfully most of the room. Great. It's this thing. It was launched in 1990. It had to get serviced by a space shuttle mission that went up there. And it's been doing a phenomenal job of taking some of our most iconic images of space over those last 35 years. We've got Pillars of Creation, some of you might recognize, M104 to Sombrero Galaxy, and so I think this was a Messier 83 over here. But some really phenomenal images, but also data that scientists have used to figure out how do these things form, and how does that inform our laws of physics here on Earth. No, who here has heard of James Webb? Raise your hand. Okay, fewer hands, still most of the room. So this one launched just 4 years ago now, basically 3.5. And it actually looks not just in visible light, well, Hubble looks at visible light, a little bit of infrared and a little bit of ultraviolet. This one looks at about half of the visible light spectrum, but then really deep into the infrared. So this one is able to actually peer through clouds of gas in space that blocks visible light and see like the inner structure of galaxies, see the inner structure of different nebulae, and also peer really far back into the universe, because as the universe expands, things move away from us, and when they move away from us, their light gets redder, basically, so we're pushed further into infrared. So James Webb is really good at seeing these objects. We also had Euclid launch in 2023. That one's been taking some amazing images, mostly in visible light to infrared, of galaxies, nebulae, globular clusters, and clusters of galaxies. I mean, in this image alone, there are trillions of stars within all of these supermassive elliptical galaxies. And Euclid has helped us understand how those galaxies move, what matter is in them, how they move around, and how these sort of things form. Then we have the upcoming Nancy Grace Roman Space Telescope, named after NASA's first head of astronomy. And it's going to be going up there and also looking at sort of visible and also infrared observations. And like James Webb and like Euclid, it's going to be hanging out at a place called Lagrange Point 2. So Hubble orbits around the Earth, right over here. But based off of how gravity interacts between the sun, the moon, and the Earth, you get these sort of like saddle points, basically regions of space that move around with the Earth and Moon, where the gravity lets you kind of hang out and not get knocked off of that spot. It's sort of like a stable equilibrium for whoever's heard that term before. But essentially, Nancy Grace Roman, Euclid, and James Webb are on this sort of tilt-hit orbit here, where they just hang out here perpetually, and the sort of interactions of the sun's, Earth's, and moon's gravity just kind of keeps them orbiting around that spot. It's really complicated math. I'm not going to go into why that is, but trust me, it works. So I've talked a lot about these telescopes and how they're going to do all this great observation in visible light and in infrared, but we haven't really gone into, well, what's over here? Why aren't we doing any observations over here? And the thing is, Hubble does do some observations in ultraviolet, down to about 19 nanometers. But the problem with Hubble is, well, that it's old. It's really old. It's 30, well, okay, by telescope standards, it's 35. So it's quite old. And the problem is that over that period of time, its electronics have been degrading, it's been accumulating damage from debris, and also it's literally falling out of the sky, because even though space is a near vacuum, there's still enough gas, about 500 kilometers up, to slowly drag it down. So it needs to boost itself back up in order to not, fall out of the sky. And it's just running out of gas at this point. So we really need something to replace Hubble, because by the 2030s, by the mid to early 2030s, it's gonna eventually fall into the ocean. So that's very sad for astronomers. We want to be able to actually still gather data in the ultraviolet, and there's a lot of really interesting stuff that actually exists in the ultraviolet. So that's a region where matter and radiation interact pretty strongly, actually. You might actually be aware of this, whether you realize it or not, every time you check the UV forecast on the Weather Channel. Turns out UV rays interact pretty strongly with the DNA in your body, actually. And they interact it interacts pretty strongly, actually, with a lot of organic molecules, a lot of molecules in general. So this region, you're going to get a lot of information about structure and composition of things based off of how much light is emitted and was interacting there. You're also going to have information about what the interstellar medium, the sort of stuff that exists between stars, the stuff that exists between galaxies. You're going to get information about what that stuff is made out of and where it came from ultraviolet light. Furthermore, Roland talked a little bit about how, 10,000-year-old star, that's a pretty new star, right? In space terms. Well, these newer stars are really, really hot, as well as really old stars are very, very hot. And hotter means that they produce more ultraviolet radiation. So by looking at the ultraviolet emissions of these stars, you get like a glimpse into how they work and how the sort of nuclear physics, how the sort of elements in these stars are interacting, and gives us an insight into how fundamental laws of physics work under pretty extreme conditions. You also have a lot of this ultraviolet emission from high energy events. So we're talking neutron star collisions, we're talking black holes and the radiation from around black holes, supernovae, the deaths of really big stars. And there's a lot of theories we have about how these objects behave, but it's not like you can just build your own neutron star in your backyard. If you can, please let me know how you can do that, because that would be groundbreaking. But we can't exactly do that in a lab here, so we need to study space to see these extreme conditions and understand how does this thing work. So that's really where CASTOR comes in. We need the UV to understand why stars explode, how do black holes get so big, what is the fate of the universe, and many more in broad terms. So what CASTOR is a replacement for Hubble's sort of ultraviolet capabilities. For the nerds among you, it has a field of view of about half a degree by half a degree, so for a total wide field of quarter of a degree, is going to be able to carry out observations simultaneously in what's called the far UV band, from 150 nanometers to 300 nanometers. The blue, don't ask me why we use U for blue. 300 to 400 nanometers, and then about 400 to 550 nanometers for the green band. So ultraviolet to green visible light. That's what we can see with this thing. And we are going to be using what's called a UV kind of CMOS sensor in order to pick up that data. And it's going to be sitting about 800 kilometers actually above the Earth, just orbiting in a polar orbit. So if you just imagine it's kind of pole to pole, rather than going in the same direction the Earth orbits, but on the axis, kind of just tilted 90 degrees around the poles, that's what CASTOR will be doing for at least 5 years, and that's the sort of time scale that we're hoping to get the minimum sort of mission objectives completed. So, this is roughly what it looks like. The whole thing isn't assembled yet, obviously, that's what we'll be talking about, but it's going to be roughly the size of a car, and it's going to be up to, I think, 700 something kilograms, being launched on one of Magellan Aerospace's I think, 200 series buses, basically. So, in comparison, really, this is what those telescopes I mentioned earlier can see. There's Roman, Euclid, and JWST, and JWST actually extends way further into this region. But they really cut off about green, and that's where CASTOR is going to be able to take over. And the great thing about it is that it actually has a really precise sort of angular resolution. The detail that it gets is going to be comparable to Hubble. There are other ultraviolet telescopes planned, but none of them have a sort of scope in terms of field of view and actual angular resolution that they'll be able to achieve. For comparison, this is how long it takes Hubble to image Andromeda, our nearest, biggest neighbor. Whereas with CASTOR, you can do it in about 6 images, because CASTOR's field of view is about 100 times larger than Hubble's, but with almost the same level of resolution. So, same level of detail, 100 times more data at a time, which is kind of a big deal for astronomers, because now it takes way shorter to get the data you want, to do your calculations and form your models. And in comparison, here's GALEX, which is another ultraviolet telescope made by NASA. I think the difference in resolution is pretty clear here. So clearly the left one is better. But that's what we're expecting to get with CASTOR. Another comparison here between CASTOR and UVEX. UVEX is the next upgrade of GALEX, but as you can see here, you can actually resolve sort of individual stars in this cluster here, while you have kind of a smudge in this one. It's just a matter of just design. These missions are designed for different purposes. Like UVEX is going to have a much larger field of view, but won't be able to get this level of detail. So, in terms of the actual science program, what that looks like for CASTOR, what is it going to do? It's going to make a lot of legacy surveys. What those are basically data sets it's going to collect over years that'll help astronomers for decades to come when they're trying to calculate either, well, I'll talk about it a bit here, but models of how galaxies form, how the universe expands, how stars evolve, sort of searches for transit between objects, but it's going to basically collect terabytes and terabytes of data over these years, and that's going to be useful for astronomers all across the world. So to lead this, we have 8 main groups: dark matter and dark energy, near-field cosmology, time-domain astrophysics, stars, galaxies, extrasolar planets, supermassive black holes, and outer solar system. I'm not going to force you all to sit through detailed explanations of what's happening with every single one of these, but in sort of a broad overview, we'll be able to study really where heavy elements come from in great detail. Like everything up until the iron, like in vehicles, for example, that comes from stars fusing it in their cores. But everything heavier than iron-60 comes from supernovae and collisions of neutron stars. And these emit tons of radiation, among them ultraviolet radiation, which we'll be able to pick up and study. And that gives us information about how the elements that are in your bodies and are in the electronics you use, how they're actually formed. Because, I mean, I kind of take this for granted a little bit in astrophysics, but think about the fact that the calcium in your bones was forged inside of a star, or that the gold, or little tiny bits of gold and silver that are in your electronics or your jewelry, those came about through either supernovae or collisions of extremely heavy stars, or neutron stars. at some point long ago, that's where they came from and eventually settled down here on Earth. They figured it was a much nicer place to live than the cold and darkness of space. So we'll be able to also probe the inner structure of galaxies. Like I mentioned, that infrared radiation is used for that. But with ultraviolet, we actually get to see a lot of the sort of high energy stuff that happens within galaxies and find out how that informs how these galaxies form. And the thing is that a lot of distant galaxies, as they get further away from us, their X-ray emissions get shifted into UV. And because of CASTOR's sensitivity, we'll be able to see in detail the sort of emissions that is coming from distant galaxies. We'll be able to weigh, roughly speaking, about 1,000 supermassive black holes across 10 billion years of our universe's history. And the data that is going to gather on these is actually going to be more data than all the previous studies of these objects combined. So it's kind of a big deal for people in this field. We'll be able to study aspects of how our solar system formed and sort of remnants from that period in time, about 5 billion years ago. We'll be able to study the atmospheres, actually, of distant planets. I mean, when I was your age, for example, at the time we had some hints that there were planets around other stars. About 14 years ago, we got phenomenal confirmation that they actually are. Tons of planets around other stars, something like 2 to 3 planets around every single star on average in the universe. And so we can even now find out a little bit about what their atmospheres are made of by looking at how their light changes when they pass in front of their host stars, by comparing that light and looking at wavelength observations, including in ultraviolet. We're able to pick out like nitrogen, oxygen, sometimes molten iron from their atmospheres. We'll be able to make a map of the sort of UV neighborhood around our Milky Way. We'll be able to use that to study our galactic neighborhood and figure out how well our models of dark matter really hold up to the actual observations. With dark matter, we're not really totally sure what it is, but we have some hints of how we think it should behave. So this will be really useful for us figuring out where do we go from here and what is this stuff. And as well, it'll help complement other observatories like the Nancy Grace Roman and the James Webb in figuring out how the sort of history of our universe's expansion has happened. Okay, this is all really cool stuff and really cool topics, but at some point along the line, someone has to build this thing. And that someone, or one of those someones, is me. So basically astronomers come up with really cool ideas of, oh, we want to study this, we want to study that, we want to get data on that, and then they tell you, make it real. And that's the difficult part. So to make it real, we have to have a very grounded approach here. And what we have in Calgary is what's called the Vacuum Ultraviolet Laboratory. It is a clean room environment, so yes, that means I have to put on a whole gown and gloves and beard net and hair net and special shoes when I go in there. And we set up this vacuum vessel essentially with 2 stages of pumping down, some roughing pumps and then a cryo pump. And the end result of this is that we can reduce the pressure to this much of a percent of like atmospheric pressure. So it's a significant decrease. Actually, I might have added 1 too many zeros here, but I'm not sure it makes much of a difference. So it's about 1/10 billionth of the atmospheric pressure. So inside of this big, almost looks like a pressure cooker, but in fact the pressure goes down. We have this device which can move in 3 dimensions, X, Y, and Z translationally, and can rotate in 2 axes to essentially move the sensor that will go on CASTOR within that vacuum vessel. And within there, we have ultraviolet radiation, which we can kind of send through all these components, bounce around through there, and aim it at the detector. And we're going to do that in order to understand how the detector works. Well, you built it, right? So shouldn't you understand how it works? Well, yes, but actually no, because you need to get data on how well it images in certain wavelengths or certain parts of ultraviolet. how efficient is it? How much noise is there at that wavelength? How well can you resolve things? Because as you'll learn from going around the other telescopes at this observatory, getting a really nice picture like the ones I showed you earlier isn't simple. You don't just get that image from one shot. You have to take hundreds of shots repeatedly, average those out. Then from them, subtract out the sort of captures of the noise on that sensor. It is hours and hours and hours of work and images that go into creating a single one of those like desktop wallpaper worthy shots before, you know, it requires a lot of work, is what I'm saying. And that's what we're trying to make easier, understand how do we accurately do that work. And while we produce the pressure in there, we're also going to cool this thing with liquid nitrogen. There's a copper heat exchanger block that goes on there. We pump liquid nitrogen in there to sort of set the temperature at about -80°C. And in doing so, we're essentially replicating the environment of near-Earth space that this sensor and this detector is going to sit in. So that's more or less what the setup looks like in CAD, if any of you are engineers here, basically. And here's, well, I say it's a sensor that goes on CASTOR. It's a small version of the sensor. The actual sensor is going to be much larger and made up of a lot of these, but this is just the sort of test bed that is going to go within there. And that's kind of behind that cable, that little sensor, this Teledyne CAS-120 CMOS sensor. So essentially what happened with it, it was developed by Teledyne. It was sent to JPL, so the Jet Propulsion Laboratory in NASA, where they sort of did, how do I put this, semiconductor magic to it. And then they sent it to Victoria, who configured the electronics, and now it's in Calgary. So you'd think, okay, we just pop it in there, we take some data with it, easy peasy done. No, because in order to make any of these missions, you have to clean your room. Everything has to be very, very, very clean, so that there's no other contamination, so that the sensor doesn't get contaminated, so that you don't have anything ruining your sensitive electronics. And that is me bent over this vacuum vessel. As another colleague of mine said, sometimes when you're working with vacuum equipment, it just sucks. Very, puns are the lowest form of humor, but I can't resist. Anyway, you have to kind of get in there and you have to clean things manually sometimes, and you have to connect a lot of very delicate wires in there. And you do this while also keeping in mind that UV light will be very easily absorbed by water vapor. Even a little bit of water vapor can reduce your transmission by 50-60% easily. So you need to make sure that whatever is in there is completely clean and that there aren't really any leaks, or minimize leaks as much as possible. You also have to make sure that you've cleaned it with acetone, with isopropanol, to reduce the sort of the oils from your fingers. We're wearing full cleaner gear here, but still you want to carry a very, very delicate cleaning of all this, because when you reduce the pressure within a vacuum vessel, things start to leak in no matter what you do. The sort of material trapped within the actual metal will start coming out of the porous structure and leaking in. So you have to take steps, essentially using electric and magnetic fields, to essentially put a sensor on there called a residual gas analyzer, to use electric and magnetic fields to figure out what do you have in there and how much of it exists. And ideally, it's clean already, because preventing contamination is much easier than removing it. But in order to get things to that point where they're good enough to send into space and you have good enough data, you have to get to baking, basically. So you wrap your device in this sort of heat tape, which is just essentially some tape with metal wires running through it, and then you turn it on to 50°C and you bake it for a week. Yeah, it's a really slow cook, I'll put it that way, basically. And that helps materials trapped in the metal sort of diffuse out into the vacuum vessel while your pumps are running and pulling all this out. I took a trip to Colorado to learn how they do it at the Laboratory of Laboratory of Atmospheric and Space Physics. They designed actually many of those NASA missions I mentioned earlier. Actually, we have a really nice poster up there. If it outgasses, we can kill it. And that's what they do, essentially. They spend a week pumping nitrogen through a system while they heat it to carry out contaminants. And then after that, we decide, okay, time for another week where they remove all the nitrogen, pump the pressure down even further to the point I mentioned earlier, 1/10 billionth of atmospheric pressure, and then they keep baking it. So this stuff works its way out, and at that point it's clean, and if you dare put your ungloved hand in there and get it dirty, you are in for a lot of trouble, because it's not easy to get rid of that. So that's what I spent a lot of time learning about and figuring out how to do, keeping things clean. And turns out that my mom's advice to keep my room clean would one day come in handy in my professional life. And yeah, that's what I learned about from all these fine folks over here. We gathered in Victoria actually last November. People from all sorts of countries, 20 plus universities. We have industry partners within Canada and abroad. Honeywell, ABB, Magellan Aerospace. We're in talk. We are actually collaborating with Lithuanian Space Agency, JPL NASA, UK Space Agency, there's an O there actually, but the Indian Space Research Organization, and we're now actually in talks with the South Korean Space Agency that was formed last year to actually launch this thing. And so we have actually partners across the entire world, all these countries and others. And this is an active discussion, an active project where everybody has their own little bit they're contributing and is working on. And hopefully by 2030, we're going to actually launch this thing. I'm also actually in this photo. I'm right there. I kind of got Mike Wazowski behind that guy's hair. But it's okay. I'm on the cover of a magazine. So, we also have a paper coming out for anybody who wants to do some light reading. We have about 40-something pages coming out in the Journal of Astronomical Telescopes, Instruments, and Systems, which I'm sure all of you just have lying by your coffee table every month, basically. So I'm actually in this author. This is the author list. That's not the whole paper. The whole thing is 40-something pages, but I'm right there. That's me. Well, there's actually been a few more names added since then. I'm the 13th author, which might not seem like a big deal, but there's 180 authors, so I think I'm doing okay. So that's where if you really want to know all the sort of nitty-gritty, look for that journal coming out some point this year, and where we go into all the actual technical specifications of how we're making this a reality and what's the science it's going to do. So, in conclusion, this is our number one priority in space astronomy. Don't take my word for it. Again, it was the Canadian Association of Astronomers that said this. And essentially, beyond the space applications of this technology, it's really helping foster a lot of growth of the space sector within Canada. And it is really an unprecedented achievement for our country, because it would be the very first time that the Space Astronomy Project, a space telescope, is led by Canada. So, at least for me, it's kind of a big deal. And I'm hoping that you'll all be excited about it too when we inevitably get some nice wallpaper background pictures for all of you to use. So, thanks for listening.
Okay, who's got a question for Nick? I got about 25, so I'm going to let you go first.
How many universities involved in this?
Oh, there's about, I think, there's over 20 universities involved in the whole project. In Canada alone, there's University of Manitoba, University of Calgary, University of Victoria, University in Sherbrooke, I think Laval, McGill. I'm not going to remember, I don't remember all of them.
Is there any Canadian university that's not involved, it sounds like?
Yeah. Hopefully Edmonton is involved. You don't know about them.
Right. Anybody else? Yes.
This moron keeps on pronouncing astronomy as astronomy.
You can pronounce it however you like. As long as you can do the science, you can pronounce it however you like, but I personally pronounce it astronomy, so take that for what you will. It's big astronomy, really trying to keep the little man down.
Okay, anybody else? Yes.
You said the Hubble was going around the Earth this way. Why would CASTOR go this way? What was the reason?
Oh, sorry. Hubble isn't actually going around the Earth this with the same rotation. It's actually on an inclined orbit as well. I don't believe Hubble is not on a polar orbit like CASTOR. So the technical reason for why CASTOR was selected to go on that orbit is, now I wasn't in the decision-making process for that personally, but they did some calculations for the field of view that CASTOR has, and really trying to get as much of the sky accessible as they can at a time. And they calculated that the sort of field of view and total amount of the sky you would have access to over the course of a year is about, I think, a third of the entire sky. So, let's see, where was this actually exactly?
Sorry, that's with a polar orbit or without the polar orbit?
With the polar orbit. I'm just trying to find the actual picture here somewhere. Okay, roughly speaking. But yeah, on the polar orbit that it'll be on, it'll be able to glimpse a third of the entire sky over the course of a year. So, and how they also considered that was the actual budget of how much time are they going to dedicate to legacy surveys, how much time will they dedicate to giving other universities access to it, to let other universities and institutions decide what they look at, and how much time will be dedicated to maintenance. So there was this is actually the paper that I mentioned, so the very specific technical details of that are in there. But that's the short answer. Does that answer your question, actually?
Way back.
How much does it cost to create something like that?
Oh, it depends. The actual I should probably do this calculation at some point. But overall, okay, so let's see. The small teams, funding for us was a few $1 million over the course of a few years. But in terms of actual total mission cost, I'd estimate a few $100 million to maybe a couple of billion. Well, actually, probably not a couple of billion. Probably a few $100 million. I can't actually give you an exact answer for that. What I will say though, to contextualize it, is that the Curiosity rover, which is about the size of a Hummer, which was landed on Mars, 14 years ago? That cost at the time, I think, something like $3 billion? $5 billion? I think it was $3 billion. The movie Avatar, which took place in space, made substantially more than actually sending a Hummer to Mars. So it can seem like a lot. I certainly couldn't afford it. But in terms of actual aggregate costs, it's actually not that much. And that's at least how we bill it to every party that we talk to, because we've had to. Well, some of our more PR-minded folks have talked to all the leaders of the major parties, and last I heard that for the past 2 years, all the leaders of the major parties have been on board with it for the last few years. So I'm not going to name any names. I'm just going to knock on wood and hope that continues being the case. Okay.
Can I ask a couple?
No.
You are testing all this in a low pressure, low temperature environment in the laboratory because you're going to simulate space conditions. So
Yeah.
the satellite needs to be very cold, yes, for the instruments to work.
Well, relatively speaking, why we make it so cold
Yeah.
is because heat is light. When you heat things up, they produce more light. That's why infrared cameras see you, because you're literally glowing, all of you right now. You're producing light because you, in physics terms, are all hot. Okay? So you're emitting a lot of infrared light. And when you cool things down, there's less light being emitted. So, and things work generally more efficiently. Now, we don't cool it all the way down to absolute zero. There's actually there's technical constraints and mechanical failures that will occur if that happens. But at around, I think, negative 80 degrees Celsius, that's where the people who did these calculations figured you'd get the most performance. And that's what we'll also test in our laboratory. Hey, how well does it actually perform at these temperatures? How bad is the noise? And by noise, I mean audio noise. I mean
My question was, is the satellite need to be cooled?
Yeah, there will be liquid nitrogen actually on this spacecraft. So there are essentially going to be electronics on there which regulate the actual sort of heat distribution throughout the satellite to keep it at its operating temperature. Like was mentioned earlier, like when you're in space is really cold. Of course, you can also get really significant like heat differentials because the side that faces the sun is going to be warmed significantly, while the side that faces away from it will be a lot colder. So we're keeping it like that.
Over by the window, you have some questions, sir. So, our atmosphere blocks a lot of radiation. How are you testing its radiation resistance compared to space, where it will be on the Earth at the moment?
Oh, okay, so you're talking about the actual radiation from the environment there. So inevitably, our electronics will degrade with time. There's nothing we can really do about that. We can, however, characterize what this damage will look like over time. If you've ever been to Vancouver, I really, really recommend for fellow nerds like me to go visit TRIUMPH, the Tri-University ASON facility. It's Canada's like national nuclear laboratory. It's what's called a cyclotron. And there, one of the facilities they have is a facility where they can bombard electronics with radiation. So they simulate the radiation in the near Earth environment, figure out how that will impact electronics, and you can do things to mitigate that. You can shield things with lead and other materials to slow down that process, but ultimately that damage is going to happen. It's just a matter of how you mitigate against it, and how you envision that impacting your work, basically. Does that answer your question?
Yeah, so obviously these mitigation things all add extra complications to your testing, because if you add lead in there or you add shielding in there, that's another element that's been put near the sensor that's going to have an effect on it, is that correct?
That depends. I mean, in the near-Earth environment, really everything that is going to go on the spacecraft is realistically going to go through multiple steps of cleaning in like very strict laboratory conditions. So really high rating clean rooms. So for example, to get rid of, we're not really concerned about lead, or for example, if there's going to be lead on this, or aluminum kind of falling off and getting on the sensor. We're more concerned about contaminants kind of baked into that stuff. So what you can do, for example, is go through an ultrasonic bath, where you essentially have these ultrasonic vibrations, shaking a vessel or a container with a special liquid like a solvent. You put your components in that solvent. It helps remove contamination from it that way, kind of clean it off. You then put that material into another bath with solvent remover, and then lastly you put it into a third bath with isopropanol typically to clean off the solvent remover. And at this point, it's about as clean as you can get it. You hopefully baked it out as well, just heated it up, and at that point you've just done as much mitigation as you can. This is why I actually traveled to Colorado to learn about how they do this, so that we can apply these techniques in our lab. So we do our best is the answer.
Yeah, I was just gonna ask how cold it is, it's real bad.
Yeah, so the actual temperature of space is a couple of Kelvin, a couple of degrees Celsius above absolute zero. So absolute zero is the coldest temperature you can get, because that's really where the atoms have no kinetic energy left. So it's only just a couple of degrees above that. But again, it depends, are you just in the shadow of an object, or do you have the sun shining on you? Because if you have the sun shining on you, you're going to heat up significantly. Yeah.
Yes.
What will happen to the Hubble over time, like in the future?
It's going to hit the ocean. Basically, it's going to literally fall out of the sky as the atmosphere, those trace amounts, drag it down over time. Like the way to get around them is just by boosting it. So it just has a little motor on it. It uses a bit of fuel, boosts itself up to a higher orbit. But it's been 35 years. It's running out of fuel. The time is nigh for Hubble, basically. So yeah.
Is there a pool on when it's going to hit the ocean? Like 1 year, 5 years?
I don't even think there's estimates. I think it's like early to late 2030s, so within a decade. So I mean, if you also want to start betting now, then I can't endorse that. But it's not going to fall on your house, probably. Probably.
There was a couple right over here. There was a couple more questions. I think. Go
own time with it to operate it, or will it be one operation that then distributes the data?
This was a thing that I thought nobody would ask me about. And here goes, like, no way any of these gonna care about this pie chart of like the time that is dedicated to all these things. I was wrong. So I have a paper over here, but essentially, there is a portion of time that is dedicated to these legacy surveys. So it's just gathering these surveys for decades to come for astronomers to use. Then, all the partner institutions, I have it here. Yes, okay. Let's see. Legacy surveys, 64%. Guest observer programs, 25%. So 25% of all the total time will be given to partner universities based on how much they've contributed to just look at whatever you want. Whatever you're interested in, just go for it. Look at this thing. And it's going to be obviously mission control or controls that probably however they set up the like IT infrastructure for it. It's like not going to be simple. Like you just press a button and it looks at this thing. But there'll be some sort of communication between different entities there, like, hey, these guys from from Open University in the UK want to look at this particular set of stars, and they'll do that. Also, 8% of the time is going to be for targets of opportunity. So just turns out some exciting event is happening, and you want to point your camera at that. Maybe, I don't know, our gravitational wave observatory has detected a signal from a black hole merger. You want to look at that. 8% of the time is going to be for that. So does that answer your question?
Yeah, and will the base be in Canada?
Yes, actually. This is also one of those things that I thought nobody would ask me about. Like there's that whole Tyrone Woods, who's one of the leads on this, he goes on and on about CASTOR and all these tools of how on the actual computer side of things, this is all going to work. The whole time I was just thinking, I just care about the hardware. I just want to actually build a thing. Turns out, people care about the IT side.
So there's just time for one more question, sir, to that.
Yeah, comparative to the web, how much more or less difficult is this to set up once it hits space?
Ooh, okay, so this one, hard question to answer. So, on the one hand, James Webb has a very complicated array of mirrors that it had to unfold and have them all working in concert in order to get images. On that side of things, it's way harder, I think, for the actual mirror setup that James Webb has in comparison to this. So that is very difficult with James Webb. But this one has its own difficulties in that infrared, it turns out there's a lot of materials that you can very easily use to reflect infrared. It's not easy at all for ultraviolet. Basically, you have significant constraints on if you use one material, what do you lose out on in that respect? So the actual manufacturing of these components, I would say, this is hard for me to answer. It's not my field of expertise. It's just that they all have their own specific challenges. But on the whole, I would say that James Webb was more difficult to manufacture in very broad terms.
So when it gets onto orbit, is it just open a thing and you go, or is it going to be 2 or 3 months of setup in space?
That I don't know for sure, but there will absolutely be some setup. You're not going to just right off the bat get good images. You have to spend time taking test images, calibrations, compare that to simulations you took on Earth. I personally figure it will be easier because of just the slower amount of moving elements and optical elements compared to James Webb. So I think it'll still be difficult. I just don't think it'll be as difficult as James Webb will. But it's not going to immediately get up and go. It's going to take a bit of time, a few months.
So listen, let's thank Nick for a great talk, and go Canada, Come on up. Nick's got a lot of energy left, so you can hit him. And I want to thank you all for taking the time to come to the observatory tonight. I'm not sure what's going on with telescopes outside. I think the sky is still clear, so we've got that last 1 minute of energy left.